Imagine a future where quantum computers work together seamlessly, supercharging scientific breakthroughs. But right now, an invisible wall keeps them apart. This is the big dilemma. Quantum systems are known for their incredible power, yet they're essentially stranded on their own islands, unable to cooperate or share information. Curious why this is such a sticking point? Let's dig in. The Defense Advanced Research Projects Agency, DARPA, the legendary innovation driver behind some of the world's boldest tech projects, is sounding the alarm for help. In a new announcement, DARPA is reaching out to innovators, tech companies, and researchers, asking them to tackle what may be quantum computing's biggest roadblock: these systems' lack of connectivity. Through its just-launched initiative, Heterogeneous Architectures for Quantum, HARQ, DARPA wants to fund cutting-edge work that will finally enable quantum machines, often built on very different technologies, to connect, communicate, and function as a unified network, not just as individual powerhouses. Here's what's at stake. Most quantum computers today rely on just one kind of qubit, the essential building block of quantum information. But, and this is the part that stirs up debate, no single qubit type is a perfect fit for every computational challenge. Imagine trying to build a supercar using only one tool. That's where quantum computing stands now. Each system is powerful, but isolated by design. For years, engineers have struggled to blend different qubit species together because quantum information is extremely fragile. Even the tiniest bit of interference or misalignment can ruin delicate quantum states. But this might be about to change. Recent scientific advances hint that integrating various qubit types into what's called a heterogeneous architecture is not only possible, but could actually boost performance. Such diverse systems make it easier to run sophisticated algorithms efficiently while lowering the bar for expensive, resource-hungry infrastructure. In plain English, quantum computers could become much faster, more scalable, cheaper to build and operate, and more accessible for solving real-world problems, ranging from designing new medicines and advanced materials to tackling urgent national security threats. HARQ's mission is divided into two major fronts. The first front zeroes in on software, specifically tools that can intelligently split complex computing tasks among multiple qubit types, ensuring that each part gets handled by the right qubit for the job. Think of it as creating the world's best air traffic controller for quantum operations. The second front puts the spotlight on hardware breakthroughs. DARPA is searching for next-gen quantum interconnects, like high-fidelity repeaters, frequency converters, and specialized memory devices that will be the invisible bridges allowing qubits of all kinds to talk and share data across distances without losing the precious quantum information. Controversial as it may sound, some skeptics question if true qubit interoperability is even achievable in the near term, given how notoriously delicate quantum states are. If you have thoughts on whether this ambitious approach is realistically within reach or just out of grasp for now, should we settle for improving single architecture machines or throw everything into heterogeneity? Share your take in the comments. You might be surprised how varied the opinions are among experts. Ultimately, DARPA is betting big on teams that can master both theory and real-world engineering, with the hope that parallel advances in software and hardware will finally knock down the barriers to scalable, practical quantum computing. The window for proposals is open until October 14th, 2025, and there's real money on the table. Individual awards could amount to $2 million during the first phase, with up to $650,000 more available for projects that show promise and need a boost for scaling up. Multiple winners are expected to be selected by February 1st, 2026. So here's the question. Are we on the verge of unlocking a new era of quantum collaboration that could change everything? Or are the hurdles just too high for now? Dive into the debate below.